So, hi. I will present you SpinalHDL, which is an alternative hardware description language for digital hardware. So, during this presentation, I will first give you a little introduction about SpinalHDL, how it comes, how we can use it, and then I will give some difference with VHDL and Verilog, and then I will give you many little examples to show you the advantage of SpinalHDL and how it is different, what it gives you, by using some abstraction and by using some software engineering approach to do hardware design. So this presentation will only be about synthesizable hardware. It's really not about a simulation thing.
But you can do it, or so is SpinalHDL beneficial to simulation as well?
You can simulate the output netlist. So yeah, to simulate generated the hardware, you can use regular tools, because the output netlist of SpinalHDL is VHDL and Verilog, so you can do the simulation of those output netlist. So yeah, this is the context. I don't have many time to give you my opinion on that, but basically what I think is VHDL 2002 and Verilog 2005 are really bottleneck in terms of engineering by many aspects, and VHDL 2008 and System Verilog will not save all of us because of EDS support, because even of features that they bring that are not so good finally. So I don't really have many time to talk about that, sorry, but so SpinalHDL. It is an open source project which starts in December 2014. It focuses exclusively on RTL description, and as you can see here, there is a flow. So you can describe your hardware by using some Scala files. Then you ask the SpinalHDL compiler to translate it into regular VHDL and Verilog that you can synthesize or simulate. And so this made SpinalHDL directly compatible with all EDA tools, because it's regular VHDL and Verilog. And you can also integrate some legacy IP, like block RAM from Glidings or from Meta, I don't know, or some more complicated things inside the SpinalHDL hierarchy by using a black boxing system. So it's quite compatible with existing flow and existing IPs. Then about the abstraction level, it starts at the same level than VHDL and Verilog, a little bit different, but the thing is then on the top of that you can build a new abstraction level. You can go away from this mess of wire, which is hardware design, to really say what you want. So yeah, just before example, some last points. So there is no logic overhead in the generated code, because SpinalHDL is not a HLS approach. It's really much more like an RTL approach as VHDL and Verilog, where you have to design gates, where you have to design registers and things like that. So there is no overhead. You will not lose performance by using it. All names and all your component hierarchy is preserved during the translation from SpinalHDL to Verilog and VHDL. So you can simulate it by using your favorite simulator. You can look at the wave and then very easily, by understanding the wave, catch up where is the bug in SpinalHDL if you have one. And basically, SpinalHDL is not really a language, and this is the main point about SpinalHDL. SpinalHDL is a language, is a Scala library. So Scala is a general purpose programming language, and SpinalHDL is a library implemented on the top of it to allow you describing your hardware. And it could seem strange to have a language into another one, but it is probably one of the best points of SpinalHDL. So I will comment that later. So yeah, this is a simple example, a very random one which has no interest in practically, but imagine you want to design this little piece of hardware with a single condition to derive some combinatorial logic, some register without reset, some register with reset, in VHDL and in Verilog, because you have to use a simulation construct to build hardware, to infer the hardware, because VHDL and Verilog were initially made for simulation purpose, not for inferring hardware. So you will have to write 3 different processes. You have a lot of redundancies because, for example, this condition is duplicated 3 times, which is not very clean, which is not very safe, because you can create bugs by having duplications. at many places. So this is how we are used to do. And this is how you can do with an hardware-dedicated syntax. And this is some SpinalHDL example. So first difference, you can define things explicitly as signals, like my register is a register not because you are assigning it into a clocked process, but because you define it directly at the definition. I want a reg of this data type. I want a reg of this data type with a reset value to 0. So because things are explicit, now you don't have to write process and these kind of things. And you can write, for example, that you want my signals to be false by default. And then when the count is true, then you can assign all of those guys in the same conditional statement. So another little example. This one is just to compare and just to understand the abstraction level of SpinalHDL right at start. So if you want to define a simple timer component, as you can do in VHDL and Verilog, it's very similar. Like you can define, it's based on Scala, so it's much closer though to software design in terms of syntax. You can define a timer class with some construction parameters. This is like a generic or a parameter in Verilog. Then this class will extend component to say this class is a component, so it's a hierarchical element of my design. Then you can define I/O into input-outputs into a bundle. Bundle is the concept of hardware data structure in SpinalHDL. Then you can define inputs and outputs of your components. It's very easy. Then you can define a counter inside your timer, which is a register of this data type. Then you can write conditions, assign it, other conditions, reassign it. So last assignment win, like in VHDL and Verilog. Then you can do assignment. So if you know how to do VHDL and Verilog, it's not so far. You can use it by the same way. It's just you don't have to care about process and things like that. But then I will start with the fun stuff. So imagine you want to have a handshake bus of color. So by handshake bus of color, I mean a stream of data which carry colors like a valid and a ready flag as arbitration and a payload as an RGB data structure. And okay, you have a source handshake bus of color. You want to queue it inside a FIFO, and then you want to connect it to the sync handshake bus of color. So in VHDL 2002, it is really kind of boring because you have to define X signals one by one. In many cases, you cannot really use records there because you want to have them parameterized by generics, so you can't really use records there in all cases. Then the most boring part is probably about instantiating the component itself, where you have to bind X signals one by one, which is very error prone, which is very copy-paste work, which is a donkey work maybe. So in SpinalHDL, things are much more object-oriented, which means, so yeah, for example, if you want, in SpinalHDL, the concept of handshake bus is named stream. So if you want to define a source stream and a sync stream, you say, I want a source and a sync, which are stream of RGB color with this parameterization. So you can already much more use data structure, which have parameterization, which have inner parameterization. You are not bound at this level. And as instance, to instantiate this FIFO, you just say, I want a FIFO, a stream FIFO, with this data type has elements which are stored by the FIFO. You don't have to bind all signals of your data structure into a single SED logic vector anymore. Then you say the depth that you want. And then this is the thing. If you want to access the push port of the FIFO, you say FIFO.io.push. You don't have to bind things. You directly have access to them by using this kind of object-oriented way. Like a FIFO is an object. You can say, I want to access this attribute of the FIFO. Then here, for example, it's written that you take the source stream, then you connect it to the push port of the FIFO, and here you take the pop port of the FIFO and you connect it to the sync. So it is better than this already, but it could be better, and I will comment on a better way to do it. So basically, stream is not something that comes magically from SpinalHDL compiler. It's something which is implemented on the top of it by using regular syntax of SpinalHDL. So it is a class with a type parameter here, which extend bundle because this class represents an hardware data structure, so it should extend bundle. Then you can define element into your data structure as a valid flag and a ready flag, a payload instance of this parameterizable type. So you can use this data structure as a slave input of your component or as master output of your component. It's not like records where you have all signals that can only be in one direction. It's not explained there how to do that, but it is really useful and easy to do. And then there is a thing. This data structure, you can add functions in it, like the operator that we have seen there to connect streams. In VHDL and Verilog, function, task, and procedure are not that much useful because inside them you can't define what you want. You have to define a relationship between outputs and inputs of the function, but you can define inside them a register, you can associate a component, you can do all the tricky stuff that you want. You are really limited with them. But here you can really do what you want, like you can define a queue function, which takes as parameter how many big you want the queue to be. And then this function will create, for example, a new FIFO internally, a new component, and then it will connect the stream on the one you are coding it to the push port of this FIFO, and this function will return the output port of this FIFO. So it is really simple, but in fact, there you go. In place of writing all this stuff, which is already better than regular VHDL, you are just writing this, like you want a source and a sink stream of RGB colors, and then you take your source, you want to queue it, we have FIFO of 16 elements, and then you connect it to the sink. And there you are starting to going away of the mess of wire of hardware design. You are just saying what you want, and this is working. You can write a bug like in that. You can do mistake in wiring. You can do these kind of things. So it's not only you can go further than, like, imagine you want to do this hardware. Like you have source stream of color. This is a random example, but it's just an example. Imagine you have source handshake, a source stream of color. You want to throw a transaction of this stream when they are black. So you need to add this arbitration gates and this check. Then from this point, you want to add a pipelining stage to have better maximal frequency or to have one depth FIFO storage, I don't know. So you need to add that. So in VHDL, probably if you have to do that, you will do it by hand, and it's really error prone. If you do error in the arbitration, it's always a lot of time to find out where is the bug in your arbitration. But here, there is how you can do it in SpinalHDL. I mean, how you can do it by using the library which is implemented on the top of SpinalHDL. Like you can define a source stream of RGB color. Then you can say, I take my source stream. I want to throw a transaction when the source payload is black. And then this function throw and will return this stage, this point, and then you say, I want to stage it. And this stage function will create this hardware for you. And then it returns this node, and then you name it sync. So really, you are saying what you want, and not how really it works signals by signals. And this is not magic here. You can do, you can navigate to the implementation of this function, and this is pure RTL implementation. It's not from the SpinalHDL compiler. So another example, state machine. So you can design state machine as you do in VHDL and Verilog by using switch statements and things like that. But you can also use the state machine tool. So state machine tool is one time again implemented on the top of SpinalHDL. It's not something integrated in it. And if you want to do this state machine, so you can say, I want a new state machine. I want state A, B, C, which are states. State A is my entry point. Then you can define some signals inside it. And then you can say state B on entry, I want to set my counter to 0. State B, when it is active, I want to count up. When my counter is 4, I want to go to state C. And then on state B, when it exits, I want to put my IO result to true. So it's just an example that SpinalHDL allows you to raise your level abstraction. But it's not because it's implemented in it, it's because its syntax is flexible enough to allowing you to build this abstraction. State machine is not magic. Really, it's just software engineering with hardware design combined together. So another example, imagine you want to do that. You have a bus like an Axilite or an APB one, I don't know. Then you want from this bus be able to drive a signal A and B, which are inside of 32 bits. So you want to have some register here which are write only from this bus. Then you do some calculation like multiplication between both, and then you want to be able to read the result from this bus. So if you want to do that in VHDL and Verilog, you will have to manage the bus timings by hand, to do some switch cases. So it could be alright, but it's not the only solutions. So here there is an example. For example, if you want to create an Axilite for bus, you can write it like that. And then you can use an Axilite slave factory tool. So this tool is one time again implemented on the top of SpinalHDL. It's not integrated inside it. And this tool will allow you to specify your register mapping by an abstract way without having any knowledge of the bus timing. Then, like you can say A is something created from the factory, has a write-only register of this data type mapped at this address. And the same for B. And then you can do some calculation here with result. And then you can say, I want my factory to make the result readable at the address 8. And so this specification here is completely abstract from the fact that it is an Axilite one. You can replace it here by an APB one, and it will work directly. So, and behind that there is a lot of software engineering, like there is HashMap that you can use to elaborate your design, and this is used behind the sensor. There is abstract classes, there is abstract functions, there is inheritance, yeah? Inheritance, exactly. And yes, there is many things that you can do. So, last example, this is just a demonstration project that I have made fully in SpinalHDL, just to check that it works correctly and it's not too much buggy. And so this is a kind of little SoC which works on FPGA with an RISC-V CPU, with instruction cache, a JTAG chain to debug it, some SDRAM controller, one chip RAM, APB bridge for low performance peripherals, GPIO, timer, UART, and VGA. This is an AXI for interconnect. This is an APB interconnect, and there is some sample of code which are interesting inside it. Like for example, to instantiate this APB bridge from AXI, like from AXI4, it's just writing that. You say I want my bridge with this parameterization, and this is done. And to instantiate all this decoding stuff for the APB with all those connections between components, it's just saying I want an APB3 decoder. My master is the APB bridge IO APB, and there you can give a list of slaves, like timer controller IO APB is mapped at this address with this address range. And you know, it's in VHDL, and in Verilog it's so boring to do that. So here it's just saying what you want and you get it. Then there is another pattern, though it is for the AXI4 side, and this one uses a data model pattern. Like you can create an AXI for crossbar factory, then you can feed it with some data model by saying, I have this list of slaves, they are mapped there, you have this list of master, and they can access those slaves, and then you say, I tell you everything, please build yourself. So you can really do software engineering to design your hardware with this approach. And yeah, this is all for this presentation about SpinalHDL. You can find everything open source in this repository. There is online documentation which starts to be good, I think. There is some ready-to-use project to help you if you want to try it, and some communication channels, so do not hesitate to comment them if you have some issue to start up with tools or anything. So this is all. Thank you. Sorry? To compare it with Chisel. So basically, I started to work with Chisel. I was happy some months with it. That was 2 years ago or 3 years ago. But basically, it appeared that there was a lot of issue with it. and like for example clock domain support, which is very badly done, and there was regularly some issue about it, but there was no move on the Scheisel stuff. So you can also find a list of things that I don't agree with Scheisel in the design on the fact section of the online documentation. And yeah, maybe Scheisel is much more about a Verilog implementation of the idea. SpinalHDL is much more about a VHDL implementation of the idea, which is with check more things and more stuff. But really, it looks like interface is the same, but really there is many differences behind the same. Like, yeah, you have to check the fact.
Okay. Yeah, we have a lot of questions. Okay, so this way, let's move that way.
So how hard would it be to make software in Scala that would run on a general purpose CPU and on some part of VHDL code? Have you ever tried such a thing, like making, I don't know, a hash map, for example, that could compile to something that runs on VHDL?
So basically, yeah, how to map some pure Scala into hardware? It's your question. Like using hash map and things like that.
Could you make a generic library that works both on
No,
CPU and VHDL?
So if you can writing software and make it able to run in hardware and software, no, it's not the case. So SpinalHDL is not an HLS approach. It's really an RTL approach where you use Scala as an elaboration tool to design what you want by saying, I want this register, I want this register, I want to do this operation. But SpinalHDL is not about translating an algorithmus into hardware. It's much more about saying what you want explicitly and you get it. But you can use hashmap to do the elaboration of your hardware. You can use all these kind of things like dynamic list, but has an elaboration tool like a for generate in VHDL or a if generate in VHDL, these kind of things.
Next, yeah.
So how do you specify the clock for a flip-flop, for example?
Yeah. So how I specify a clock for a flip-flop? So basically, it's much better than VHDL because it is implicit. So you can define area of your design which are under the effect of a given clock and reset configuration, and then everything inside it, all subcomponents will automatically get it. So yeah, I had a slide, but I haven't the time to talk about it.
There will be a discussion session after 2-3 talks after this, so we'll have more time to discuss maybe in more depth these kind of things. More questions?
Yeah. I've used a few of those tools that wrap, let's say, a VHDL languages. I wonder what kind of error message do you get when it doesn't work?
So which error message you get when it doesn't work? So basically, you have much more confidence when you generate the SpinalHDL netlist. You have then much more confidence than it's working physically in for real than a handwritten VHDL one, because SpinalHDL do a lot more check by default than it do a lot of check directly than, like for example, if you check that you don't have control loops, it will check that you don't have with mismatch, these kind of things. And if you have an error, it will print you where in your SpinalHDL description there is something wrong. It will give you the name of the signal. So really, it's maybe even less easy than VHDL to remove bugs from a SpinalHDL description, because yeah, so it checked a lot of much more things, and I put a lot of intention to have nice printed error message with the print stack of the execution of the SpinalHDL description and these kind of things. So it's not really messy. All right. Have to try to get a good idea of it.
Okay, how many questions do we have? Because we're really running out of time. So 1, 2, 3, 4, 5. It's gonna be too much, guys. Can some of the questions be put in the discussion session afterwards? Is anybody going to stay among you? No? Okay, go ahead.
Yeah,
Try to be quick, please.
Quick question. Yeah, at the beginning of the presentation, you said you're mainly going to focus on synthesizable logic.
Yeah.
And then I'm just wondering, just curious. Slide 7, if you can go real quick.
Yeah.
My signal falls. How is that going to translate into something that is sensitized?
So there will be 3 processes generated from it, exactly like there, exactly the same.
Okay, so it's just a direct.
Yeah.
Okay.
But how do you distinguish between blocking and not blocking?
Sorry?
How do you distinguish between blocking and not blocking?
SpinalHDL all is how to distinguish in between blocking and not blocking. So in SpinalHDL by default it is I don't know which is one, but it is like the default, well, like this one here. Yeah, you can do the other one by using another syntax too.
And just also translation question, a similar thing. You had a multiplication somewhere, right? How is that translated? How much control do I have over that?
So how the multiplication is translated into VHDL, exactly the same than in VHDL.
Okay.
So then if you want to use FPGA dedicated blocks and things like that,
Okay.
you can instantiate a black box, or you can try to write it by the way at the synthesis tool where you understand it. But there is no magic between in the translation, so it's one-to-one.
Yeah, so if I don't trust SpinalHDL, is there any way to make formal verification against what I have as SpinalHDL and what I have as
So if you about formal verification between the input SpinalHDL and the output, there is no formal verification about it because basically it's not required because you are verifying the output netlist. You are not doing your verification stuff on the SpinalHDL description. You are verifying the VHDL generated files. So it's why I don't really care about it being formal. But I have a good confidence in the translation process.
It's a way even